Now coming to the kinetic gas equation. Kinetic gas equation we get it from the kinetic what you can say molecular theory, we can say that, of matter. Already we have discussed the kinetic molecular theory of matter, the kinetic molecular theory of postulates we have discussed already. From there we get the kinetic gas equation. Now the kinetic gas equation is this, that is PV is equal to 1 by 3 mnc square, where P is the pressure of the gas, V is the volume of the gas, M stands for mass of each molecule of the gas. Write it down what I am saying. Alright. P is the pressure, V is the volume of the gas, we can say that in that particular container. M is the mass, M stands for, small m stands for mass of each molecule of the gas, each molecule. N stands for number of molecules of the gas present in the container. Alright, the total number of molecules of the gas present in the container and present in the volume V. N stands for total number of molecules of the gas present in the volume V. That's the volume of the container, isn't it? And C stands for root mean square speed, we can say that, or root mean square velocity, which we call it as RMS. RMS stands for root mean square speed or root mean square velocity, we can say that. Clear? So we'll discuss what is this root mean square speed or the root mean square velocity of the gas, we can say that. Again repeat, P is the pressure of the gas, V is the volume of the gas in the container, M is the mass of each molecule of the gas, N stands for number of molecules of the gas present in the volume V or in the container, we can say that, and C is the root mean square speed or the root mean square velocity, we can say that. Clear? So what is root mean square speed? What is root mean square velocity? Write it down. You can write it down also. Root mean square speed may be defined as, from the word, if you just what you can say that before going to the definition, you just simplify the word. Alright, you will get the answer. You will get the definition. Root mean square. Root means square root. Mean means average, and square we have to square it. Alright, that's it. That is what I am saying in sentence. You see that it is defined as the square root of the mean. The square root of the mean of the square of the speed of different molecules of the gas present in the container. It is defined as the square root of the mean of the square of speeds of different molecules of the gas present in container. That is said to be as root mean square speed. Means, suppose we are having C as the root mean square speed. So I said you, it is the root. Alright, let us say we are having N1 molecule whose velocity is V1, so square, plus N2 molecule whose velocity is V2, so square, V2 square, plus N3 molecule velocity is V3 square, plus dot dot dot, we can say that, divided by, now I want to find the average or the mean. Mean means the average. What will I do? I will add it to the number of molecules. So here the number of molecules is what? That is N1, N2, N3. So here also same thing, N1, N2 plus N3 plus dot dot dot. I said it. It is the root of, it is defined as a square root, this is square root, alright, of the mean, this is the mean, average of the squares of different velocities, alright, of the gas, of the different velocities of the different molecules of the gas present in the container. Alright, so this is your root mean square speed or the root mean square velocity, we can say that. Clear? Fine. Now, let us say here M into N. M stands for what? I said mass of each molecule of the gas, and N stands for number of molecules. So definitely if I multiply M into N, I'll get, that is capital M. Capital N stands for what? That is molar mass. Definitely. Number of molecules into, that is mass of one molecule will give you what? That is the molar mass, that is mass of 1 mole of a gas, we can say that. Clear? Mass of 1 mole of a gas. Now all this is measured at standard conditions, mind it. All these which I am saying, the kinetic gas equation and all these values which I am saying, all these are under standard conditions. Remember this particular thing, don't forget. So M stands for here, that is a molar mass or the mass of one molecule of the gas. So hence I can write this one as PV is equal to 1 by 3 mc square. Is that right? mc square. PV is equal to 1 by 3 mc square. or C is equal to, that is 3 PV by M root over of. C is equal to 3 PV by M root over, we can say that. Now, for 1 mole, alright, for 1 mole, ideal gas equation is PV is equal to RT when N is equal to 1 mole. Because ideal gas equation is what? PV is equal to nRT. Now when N is equal to 1, PV is equal to RT. So now instead of PV, I can write root over of 3 RT by M. See here, PV is equal to RT. So instead of PV, I put it as 3 RT by M. Fine. I can also write this equation. I'm writing it here. I don't have the space. Now M by V is what? Mass by volume is what? Density. So V by M is 1 by D. Reciprocal. Alright. So I can write it as, that is 3P by D. This also I can write it down. Isn't it? I can write it as 3P by D because V by M is 1 by D. See, instead of V by M, what I put it? 1 by D I put it, because M by V is volume, mass by volume is density. So reciprocal V by M, it will be 1 by D. So C is equal to root over of 3P by D. We can say that. So this is your kinetic gas equation. This is the main equation from where I derived all these things, so to say. Clear? So now I got it. That is C is equal to root over 3P by D or root over 3 RT by M or root over 3 PV by M, so to say. Now, next, one of the postulates of the kinetic molecular theory of gases, it says that when the temperature increases, got it, the velocities of the gas molecules also increases. That is, velocity of the gas molecule depends upon the temperature. Alright, one of the postulates. I am reading it out, that particular postulate. The molecules are moving with different velocities. You know that. Suppose in a container, different molecules are there. So they are moving at different velocities. Alright. They possess different kinetic energy as a result, because kinetic energy depends upon velocity. How? Because kinetic energy is half mv square. So velocity is different. Kinetic energy will be different. Definitely. They possess different kinetic energy. However, now listen carefully. However, the average kinetic energy of the molecules of a gas is directly proportional to the absolute temperature of the gas. The average kinetic energy, the kinetic energy, we are calculating the kinetic energy, which is half mv square. Now when we calculate the average kinetic energy of the gas molecules, we cannot calculate the kinetic energy of each molecule. No? That is not possible, because there are innumerable molecules of the gas present in a particular container. So hence we on an average we say, see, this is the kinetic energy of the gas molecules present in the container. So when we say kinetic energy of the gas molecules present in the container, we mean to say the average kinetic energy. Alright, we mean to say the average kinetic energy. Listen carefully. So the average kinetic energy of the molecules of the gas is directly proportional to the absolute temperature of the gas. So Ke, that is kinetic energy, is directly proportional to temperature. That is what I said. So kinetic energy increases with an increase in temperature. Now this thing I have to prove it now. Alright, this is being said in one of the postulates of the kinetic molecular theory of gases. One of the postulates of kinetic molecular theory of gases. I have to prove this. By the help of the kinetic gas equation, I have to prove this particular thing. Alright, now see here. Now I have said you PV is equal to 1 by 3 mc square, I said, or I also wrote it as PV is equal to 1 by 3 mnc square. Is right? Where mn is equal to nothing but, we can say, that is mass of 1 mole of the gas. We can say that. Now I can write this one as, instead of 1 by 3, can't I write in this way? PV is equal to 2 by 3 into half mc square. 2 will cancel and it will be, what you can say, 1 by 3 only. Alright, this one I can write it this way. Now, what is half mc square? It is nothing but kinetic energy. So, I can write PV is equal to 2 by 3 Ke. This is very important. PV is equal to 2 by 3 Ke. We can say that. Clear? So, now we have seen it. For 1 mole of the gas, PV is equal to RT. For 1 mole, just now we have done it. PV is equal to RT. So, we can say RT is equal to 2 by 3 Ke. For 1 mole of the gas, for 1 mole, ideal gas equation is PV is equal to nRT. But when n value is 1, PV is equal to RT. So RT instead of PV, I can write RT. I wrote it in the previous one. So RT is equal to 2 by 3 KE. We can say that. Clear? Or KE, I can say, is equal to, that is 3 by 2 RT. This is, we got it. This is the kinetic energy. Now if I want to calculate the average kinetic energy, listen now, average kinetic energy. So average kinetic energy, I will take it as KE bar. How will I get the average kinetic energy? I will, what I can say, divide it by Avogadro's number. I will divide it. This is Na. Here Na is your Avogadro's number. This you can see. 3 by 2 I have divided by Avogadro's number. When I am divided by Avogadro's number, what will I get? I will get the average kinetic energy of the gas molecules present in the container. The average, because here I have taken that is nothing but M stands for the mass of 1 mole of the gas. No? So 1 mole contains how many molecules? Avogadro's number of molecules. So hence I have divided by the Avogadro's number to get the average value. So 3 by 2 KE dash. KE dash stands for your average kinetic energy. So average kinetic energy is equal to 3 by 2 R by NAT. Now what does that this R by NA stands for? So R by NA. Na is Avogadro's number, stands for K. K stands for Boltzmann constant. K stands for Boltzmann constant. We can say that. And if we put the value of R, got it, we are having different values of R, we can say that, different values. Let us say I am using the SI unit. The value of R is 8.314 joules per Kelvin per mole. And Na is nothing but 6.023 or 6.022 in 10 to the power 23. You know that, Avogadro's number. Then if I put this value, got it, if I put this value, that is 8.314 divided by 6.023 in 10 to the power 23, I will be getting to be as on division 1.38 into 10 to the power minus 23. Got it? 1.38. The value of this will be 1.38 into the power minus 23 joules per Kelvin in SI system. See, the value of R, we have got different values of R depending upon different units. I have already discussed with you, different units, they have got different values. But in SI system, this, when I take R as 8.314 joules per Kelvin per mole, and this is 6.023 into 10 to the power 23, I will be getting this particular value of K. Otherwise, when the value of R will differ, this value also is going to differ. Clear? This is an SI system, I said it. Now, what you got it? Average kinetic energy, we got it. This is nothing but, I can say KE dash, I can write it as the average kinetic energy, KE dash, I can write as 3 by 2 KT. Isn't it? R by Na is K, Boltzmann constant, so 3 by 2 KT. Now, what I said, this is your Boltzmann constant. This is a, if of course it's a number, it's a constant, it's a scalar quantity. That means Ke is directly proportional to T. This is a constant, definitely. So Ke, of course, average kinetic energy here, it is directly proportional to T. That is what I have to say, because I said you in one of the postulates. Just now I said the average kinetic energy depends upon, is directly proportional to the absolute temperature of the gas. That means if temperature increases, kinetic energy is going to increase. Alright, and temperature decreases, kinetic energy decreases. Definitely, we proved it. So average kinetic energy is directly proportional to temperature. So here we have proved one of the postulates of the kinetic molecular theory. Now if you want to still go in details, got it, then we can go still in details. Now kinetic energy, you can say it is nothing but half mc square. See, half mc square is kinetic energy. You can take capital M also, no problem. So is equal to, this is a kinetic energy, is equal to nothing but T. Is that right? So here instead of kinetic energy, I can write it as nothing but half mc square is directly proportional to T. Okay, you can write directly proportional also. Now for a particular gas, got it, for a particular gas, the mass remains constant. If you are getting confused, I am writing it as capital M, no problem. For a given gas, for a particular gas, the molar mass is constant. Half is also constant. So as a result, what you can say, C square is directly proportional to T, or C is directly proportional to square root of absolute temperature. We can say that. That is directly proportional to the square root of absolute temperature. So if T will be 0, then C also will be 0. So when the T will be 0, what I said you? Absolute temperature. Absolute temperature is what? Absolute temperature is that particular temperature is the lowest attainable temperature attained by a gas, where the molecular motion ceases to be 0. Alright, where the molecular motion ceases to be 0. So when T is 0, C is also equal to 0. That means here when the temperature is 0, the absolute temperature is 0, the molecular motion also is 0. Molecular motion means velocity becomes 0. So that is also we have proved it. Alright, that also we have proved it, which you have studied in the lower classes theoretically. That an absolute temperature, absolute 0 is how much? Minus 273 degrees Celsius, which is known as 0 Kelvin. Alright, so at absolute, what you can say 0, the molecular motion ceases to be 0, we can say that. Means kinetic energy of the gas is 0. We have proved it. That if this is 0, then this is also 0. Alright, this also is 0. So molecular motion ceases to be 0, we can say that. So it implies that the beyond this particular temperature, the liquefaction of the gas takes place. So as already I said you, it is the lowest attainable temperature attained by any gas. No gases attain this particular temperature. That also let me say you, no gases attain this particular temperature. Hence Lord Kelvin has said that is the lowest attainable temperature attained by any gas, because beyond this temperature what is going to happen? It is going to get liquefied. The gas is going to get liquefied. The liquefaction of the gas takes place. Alright, so this is about your kinetic gas equation and about the postulates. I have explained it on the basis of the kinetic molecular theory of gases. Fine. So you also learned it about the root mean square speed or the root mean square velocity. Now, next we'll come to the next type of velocity is your average velocity. See, different that is velocity. I said you already that in a particular container, different molecules of the gases are present. Alright. They are bombarding with themselves and also they are bombarding with the walls of the container. Alright. So hence they possess different speed. We can say that. Clear? So here we need to calculate another type of speed, which is known as the average speed or the mean speed. So how do we calculate the average? Very simple. Like in maths, how do you calculate the average? We take the number of molecules into the velocity divided by the total number of molecules. Alright. It's the arithmetic mean of the speeds of the different molecules of the gas. It is simply the arithmetic mean. I said, in maths you study the arithmetic mean. How do you find the arithmetic mean? For examples, our average speed is denoted by C bar dash, we can say that, or C bar, I should say. Better is to say C bar. So let us say we are having N1 molecule, whose velocity is V1. We are having N2 molecule, velocity is V2. We are having N3 molecule, velocity is V3, plus dot dot dot. By total number of molecule is what? N1 plus N2 plus N3 plus dot dot dot. This is known as the average speed. Simple. Just like in maths, we find it out. Alright. So in this way, we are having the average speed measured in this particular manner. It's very simple. Alright, the average speeds. From the name itself, we can understand the definition. From the name itself, if you simplify the name, because it's not that you haven't studied all these names. It's a new term for you. You have studied in the lower classes. You have studied. Just we need to understand it on that particular basis. For that reason, I am telling you. Okay. Now, according to the kinetic molecular theory, got it? According to the kinetic molecular theory, we can also say that C dash, we can say that C bar is equal to root over of 8RT by pi m. There we got, in case of root mean square speed, RMS speed, we got it root over of 3RT by m, isn't it? Here it is root over of 8RT by pi m. This is calculated experimentally. Got it? Fine. So this is about your average speed. Now, next speed we are going to come to is the most probable speed. Most probable speed. Now, just now I was telling you that Maxwell and Boltzmann. You have seen here Boltzmann constant. I told you. So Maxwell and Boltzmann, these two scientists, they observed it that suppose when in a particular container, that is a given volume of gas is there. So that given volume of gas contains different molecules. Different molecules are there. Now why do I say different molecules? Because at the same temperature, at a particular temperature, these molecules possess different velocities. Alright, listen carefully. In a particular container whose volume is V, alright, volume of the container is V liter, let us say, at a particular temperature, constant temperature, we can say that. So there are different molecules present. Now different molecules have got different speeds. Alright. These molecules, now why they have got different speeds? Because these molecules not only collide with themselves, but also they collide with the walls of the container. Hence, they acquire different speeds. They have got different velocities. We can say that. Now, so Maxwell and Boltzmann, they draw a graph, got it? And they showed us that as a result of collisions of these molecules with each other, as well as with the walls of the container, we are able to calculate the average speed of the molecules, which I already studied, root over of 8 RT by pi m. Similarly, if you calculate the fraction, listen carefully, if you take the fraction of the molecules, then we are also able to calculate the most probable speed of that particular molecules. Again I repeat, if you are taking the fraction of the molecules, fraction, how do you take the fraction of the molecule? Delta n by n, we can say that the number of molecules is n. Delta n is the number, change in what you can say, there is a number of molecules, so that's called the fraction. Fraction means something by something now. So delta n by n, we can say that I am taking. So when I draw a graph, alright, this sort of, now this graph was given by Maxwell and Boltzmann. Here I am taking delta n by n. N stands for Avogadro's number, let us say. So here this is known as fraction of molecules. This is a fraction. You can see this is a fraction, isn't it? Fraction of molecules. And this is your molecular speed. Molecular speed. And let me write it clearly here, otherwise you will be confused. Fraction of molecules. You can see that. Clear? I have taken in the y-axis, and the x-axis I have taken the molecular speed. So I studied that is Maxwell and Boltzmann. They said that. However, they said that as a result of collision between themselves, as well as the result of collision between the container. Got it? So what on the walls of the container? On the container means on the walls of the container, some of the molecules they increase the speed, and some of the molecules they slow down their speed. Alright? Some of the molecules the speed increases, and some of the molecules they will slow down the speed, definitely. Alright, hence the fraction of molecules possessing, listen carefully, hence the fraction of molecule possessing a particular speed remains constant at a constant temperature. The fraction of molecules, they will have a particular speed at a constant temperature, isn't it? Some will have more speed, some will have less speed, but a particular fraction of molecules you will find they have got a particular speed at a particular temperature. Alright, a fraction of molecule possessing particular speed are plotted against what you can say, that is the speed of the molecules, then we will get a graph, and this sort of graph you will be getting it, and from here you will be finding it out. So this is the maximum fraction of the molecules now. So they possess a particular speed. This is speed. This particular one is a speed, because in the x-axis we have taken the molecular speed. Now this is what I said, denoted with the letter C star. And what it represents, what I said, the maximum fraction of the molecules possess this particular speed. See the graph? This point represents the maximum fraction of the molecules, isn't it? It increases, and after that it decreases. So these points represent the maximum fraction of the molecules. And what is the speed? This is the speed of the maximum fraction of the molecules. So what is this speed known as? This speed, C star, represents what? C star represents the most probable speed. Definitely. Because this is the speed this particular speed is possessed by the maximum fraction of the molecules. Means in a particular container, as I said some of the molecules will have lower speed, some of the molecules will have higher speed, but a fraction of molecules will have a particular speed at a particular temperature, and that particular speed is called as the most probable speed. So Maxwell and Boltzmann, they calculated it from a particular graph. They did the experiment, and from the graph they calculated and they represented this particular speed at the most probable speed, they said it. And you can see it also from the graph. Alright, so hence this particular one, most probable speed, is known as C star. So how do we calculate then the most probable speed? I think definition you understood. That is, most probable speed definition is, it is the speed possessed by the maximum fraction of the molecules, or the maximum number of the molecules, we can say that. Clear? At a particular temperature is called as the most probable speed. I hope you understood. The peak of the graph which shows the maximum number of molecules, they possess a particular speed. This is called as the most probable speed, we can say that. Clear? And here the most probable speed can be calculated by using this formula: C star is equal to root over of 2 RT by M. Got it? Root over of 2 RT by M. So we got it. C is equal to as the what you can say RMS speed, which is root over of 3 RT by M. Then we got C bar, which is the average speed, which is root over of 8 RT by pi M. And then after that we got it the most probable speed, that is your C star, which is represented by, which is equal to root over 2 RT by M. So let me tell you, all these are calculated values. It has been calculated experimentally, all these values are. Got it? Now if you that is find a relationship between them, you will be getting, that is C star is to C bar is to C. You put the values: C star root over of 2 RT by M, C bar is root over of 8 RT by pi M, and C is equal to root over of 3 RT by M. You will be getting 1 is to 1.128 is to 1.224. You can put the value and you can divide it and see it. Alright, you can put the value. First you divide this 2, you will be getting this. Then divide this 2, you will be getting this. Then you get a relationship. Alright, that is 1 is to 1.128 is to 1.224. This is a relationship between that is the most probable speed is to average speed is to the RMS speed. You can find it out. You can see it and you can find it out. Alright, now next is, after that, Boltzmann and Maxwell also said that upon the nature of the gas, the most probable speed differs. Upon the temperature of the gas also, most probable speed differs. How? Alright, okay, fine. Now let me complete this graph. Little bit more I have to say about this graph. Let me complete it. So as I said you that we have got a relationship, isn't it? We have got a relationship. Let me write it. By mistake I rubbed it, this one. So that is on this particular graph, what you saw is that is C star is to C, C bar is to C. We got it 1 is to 1.128 is to 1.224. Got it? So hence you will find it out. This represents your C star. Now in between this, if I draw a graph, this one is yours nothing but this is your C star. Then this is your C bar, and this particular one, it represents your nothing but C. So this is your average speed, this is your most probable speed, and between the average and the most probable speed you get the this is your RMS speed. I'm very sorry, this is your RMS speed, root mean square speed. This is your most probable velocity or most probable speed. So in between the most probable speed and the RMS speed we get the average speed. We get the average speed. Alright, the average speed lies between, definitely average will always lie between the most probable speed and the, what you can say, the RMS speed. Alright, so we can show from this graph in this particular way. Let me rub this one because already I have written at the top. So let me draw this one properly. This point represents the average speed, this point represents the most probable speed, and this point represents the RMS speed, we can say that. From this graph we can say this was the graph which was given by Boltzmann and Maxwell. Experimentally they found the value and they gave us. Now we'll come to what is the effect of, what you can say, that is most probable speed upon the nature of the gas. Alright, means what you find is that it is seen that lighter gases with molecular mass, with a lower molecular mass, got it, will have higher value of most probable speed. Definitely lighter gases will move faster, so they will have higher value of most probable speed, because lighter gases, they will have more speed, lighter gases, compared to the one which is heavier. Alright, compared to the one which will be heavier. That means these gases will have more, will move faster. Lighter gases definitely is going to move faster. So they will have the more maximum most probable speed, we can say that. Try to understand. So for example, I am taking the lighter gases as chlorine and nitrogen. Now, lighter gases I am saying, sorry, I am taking two gases as chlorine and nitrogen, in which nitrogen is a lighter gas and chlorine is a heavier gas. So nitrogen molecule will possess a higher most probable speed than the chlorine molecule. Again I repeat, I have taken two molecules, one is chlorine, another is nitrogen. You can take any other molecule, you can take oxygen and chlorine, you can take oxygen and fluorine, alright, you can take any two molecules, you can take it, just to compare. So this depends, I am talking about the nature of the gas, mind it. So one is heavier, another is lighter. So which is heavier here? Definitely if I take chlorine and nitrogen, chlorine is heavier. Got it? Molecular mass is 35.5 into 2, that is 71, and nitrogen is nothing but 14 into 2, it is 28 grams. So definitely nitrogen is lighter than what you can say chlorine. So as nitrogen is lighter, it is the lighter gas. So this gas will move faster. Alright, definitely compared to chlorine. So this particular gas, that is nitrogen, will have more probable, what you can say, will be having the highest, or will be having the higher value of most probable speed than that of chlorine. What I said, nitrogen will have higher value of most probable speed than that of chlorine. We can say that at a particular temperature. Remember that at a particular temperature. I am talking about a constant temperature. Mind it. Clear? That means if I am drawing the same graph I am taking here, I am taking molecular speed, and here if I take delta n by n, there's a fraction of molecules. Of course, it depends upon that only. So what you will find is that, suppose this is a graph for chlorine. This is the most probable speed of chlorine. We can say this is for the chlorine molecule. Alright, this is for the chlorine molecule. I got it the most probable speed. Clear? Let me write chlorine here, that's better. That is Cl2 at a particular temperature. Temperature remains constant. Alright, now this is the most probable speed. We can say that. The most probable speed for chlorine, I got it here. That is, let us say C star 1. Okay, for the chlorine. Now, for the, what you can say, for the nitrogen, I got this sort of graph. This sort of. That is, let us say nitrogen. So hence, let me do it properly. For the nitrogen, I got this sort of graph. So definitely this is the most probable, this is the maximum fraction of the molecules possessing the speed. Alright, so this is the most probable speed. Now this is, let us say C star 2. This is for what? Nitrogen. So you can see very clearly the molecular speed of nitrogen is much more than that of chlorine. This is for the chlorine, C star 1, and C star 2, this is for the nitrogen. So nitrogen possesses, as a lighter molecule, it possesses higher most probable speed than that of what you can say chlorine. So that means lighter gases will have higher most probable speed than that of the heavier gases, we can say. Similarly, if I increase the temperature, now here the temperature was constant. Now if I increase the temperature, then what you will be getting it? You will be getting two, that is, let us say here, that is, I am keeping the gas as constant and I am taking different temperatures. Let us say this one is T1 and this is T2. I can take another one also, that is, let us say this one is your T3. I can take another one also. This is, let us say, T3. C star 3. I can take another one. No problem. I can take another one also T4, but I don't have the space. I am not taking here. So you will understand here also. So here what you will see, T3 is greater than T2 is greater than T1. Alright. So as the temperature is increasing, now listen carefully here. As the temperature is increasing, the most probable velocity is also increasing. Most probable speed is also increasing. Because already we have studied, with increase in temperature, the velocity increases. Because we have seen C is directly proportional to root over of T. Alright, whether it is root mean squared speed, whether it is most probable speed, whether it is average speed, speed increases ultimately with increase in temperature. So what you find is that with increase in temperature, the speed is also increasing. That is number one. Alright, so the peak shifts forward. The peak of the graph, see it is here, now it's here, it is here. The peak of the graph is also shifting, it is forward. The peak of the graph, you can see it is shifting forward, showing that the most probable velocity also increasing. Definitely, the peak is shifting, so the velocity is also shifting, velocity is also increasing. Clear? Then the peak of the graph, that's the whole curve, shifts downwards. Alright, you can see it is shifting downwards. For T1, T2, T3, you see it is shifting downwards. Alright, showing that the fraction of molecules or the number of molecules possessing the most probable velocity decreases. Definitely. That is, the number of molecules which possess the most probable velocity is decreasing. Here the fraction of molecules is this. Now as the temperature increases, fraction of molecules is this. As the temperature still increases, fraction of molecules is this. So the number of molecules participating in the most probable velocity also decreases. But the most probable velocity increases. But the fraction of molecules which is participating, that is decreasing. From the graph you can see it there. Nothing I am hiding there. Now the curve is becoming flattened. It becomes broader in the middle. See, here it's almost flat. The graph is in the middle. It is almost flat. Got it? Showing that more molecules have speed that is near to the most probable speed. When the graph becomes flat, it means what? That the more number of molecules is having the most probable speed, because here the graph is almost flat. That means this area, all these molecules is having the speed which is the most probable speed, I can say that. The fraction of molecules having higher speed increases. Yeah, the fraction of molecules which is having higher speed, the most probable speed is increasing. It is increasing. Number of molecules is increasing. The fraction of molecules having lower speed decreases. Lower speed, the fraction of molecules is having the lower speed, it is decreasing. See, this is a lower speed. Alright, this is C3 is higher compared to C2 and C1. So C1 is having the lower speed, it is decreasing. Alright, so these are the conclusions we can draw from this particular graph. So we came to know about the kinetic gas equation, we came to know about average speed, molecular most probable speed, as well as the RMS speed. Thank you.